Okay. Hi, everyone. Welcome back. Thanks for coming to the last talk of the workshop. Yeah, so I guess, so last time we saw the definition of spectral independence, and I proved to you that if we have spectral independence for all conditionals of the distribution, namely for every possible fixing of any subset of the coordinates, that it is spectrally independent, that then you have rapid mixing of a simple Markov chain like Glauber dynamics. Okay? So in this lecture, I want to show you two very different methods for proving spectral independence for an interesting sampling application. So we're going to be taking as our main example in this lecture to be the following distribution. So it's going to be distribution over matchings of a graph. So, okay, so let G be a graph, and we're going to let, let's say, fix a lambda, and we're going to let mu be a distribution over all subset of edges that form a matching. So for all matchings. Okay, and in particular, I'm not just looking at the perfect matchings, I'm actually looking at all matchings. So this includes the empty set, for instance. Okay? This is actually a special case of the hardcore model, or the independent sets that we saw in the previous lecture. Okay? But I want to prove to you, so the theorem I want to prove to you is that, so let delta be the maximum degree, okay, which you think of as being constant. Then mu is spectrally independent with, let's say, polynomial in lambda and delta. Okay. Oh, sorry. Okay, I want to prove this to you in two different ways to illustrate two very different techniques for establishing spectral independence. Okay. Okay. Oh, yeah.
This, I guess, matchings of all sizes was that was done by Sinclair and Jerome.
That's right.
In the 80s.
Yeah. So there's a very classical result of Jerome-Sinclair, which proves that for any graph, even without the bounded maximum degree restriction, that Glauber dynamics mixes in polynomial time for any fixed value of lambda, using a very different technique called canonical paths. Okay? So if you plug this into this theorem, it would not give you a better result. I mean, first there's a dependence on maximum degree, and also it would give you quite a large polynomial in the running time. If you plug it into some of the more refined mixing results, where you, the more refined results that show spectral independence implies optimal mixing, you can get a better dependence on n, but the dependence on, again, maximum degree and lambda are pretty bad. Yeah. I think there are some more recent results which show that in some very special cases, you can actually remove the dependence on delta here, and I think it's still open, for the general case. But yeah.
Okay. The main point of this example is pedagogical.
It's more pedagogical. Yeah. This is not like a new result, a mixing result by any means. Yeah. Right. So if you make some more assumptions on the structure of your distribution, it comes from, let's say, independent sets on a graph, or some kind of model on a graph in which you have some conditional independence properties, then you can make this n log n, and it'll be the maximum degree to the power of the spectral independence constant. Okay. So the dependence on n will be optimal, but then you still have some constant some exponential dependence on the spectral independence parameter. Yeah. Good. Okay. So now I want to talk about the techniques, or really two very different techniques, and I think they're both quite beautiful. And so I thought, so hopefully that might be also useful and interesting to you all. So they'll be based off of, so there are two techniques. So the first half will be about coupling, or maybe what I'll call like disagreement percolation. And the second is based off of geometry of polynomials, or more precisely, zero freeness. So let's do each one in turn. Okay, so let's look at disagreement percolation. So here's an observation. So let me just say at the outset that, at least for the purpose of the lecture, we're going to bound something stronger than the max eigenvalue. We're going to bound the maximum row sum. Okay, so I'll say right here, this lecture will bound the maximum over all I summation over j of the absolute value of the influence of I onto j. Okay, so it's like the matrix norm induced by the infinity vector norm. Okay, from this, I'm going to further upper bound this. I want to interpret this as some kind of like distance between the distribution where I condition on the value of coordinate I to be 1 versus the distribution where I condition on the value of coordinate I to be 0. Okay, so here's an observation, which is that, so let me just call this like this quantity star just for convenience. So star is upper bounded by the infimum over all couplings gamma of these two conditional distributions, one in which I have, assume I is pinned to 1, and the other where I assume I is pinned to 0, of the expectation whereby I sample a random pair configurations from this coupling and look at the Hamming distance between them. Okay. So I'm not going to write down like the proof of this. It's actually quite simple. The way you prove it is you just view this influence as the total variation distance between the marginal of j, condition on I, where I look at the two possible conditionings on I, right? And in this sum, you're allowed to choose a different coupling for each choice of j. Here, I'm allowed to choose just one coupling for all of the coordinates, and that's essentially the proof. Okay. So what this allows me to do, or what this reduces the problem to, is I want to now just construct a coupling of these two distributions such that in expectation I have small. Sorry. Yeah, so I guess here, let's say about like for all I here, yeah, let's just say like for all I. Yeah, and this thing. Okay. It's okay? Yeah. Oh, sorry, yeah. So this is so you think of this as being like this is a distribution on pairs of configurations x and y such that marginally x is distributed according to one of them, and the other one is distributed according to this one. Right? So think about it as like a joint sampling process for this pair of distributions. Okay. So in the matching example, what we're going to do is we're going to construct this coupling iteratively by like a local algorithm. Okay, and let me just illustrate say what this algorithm is going to do. Sorry, yeah, this is Hamming distance. Yeah. Okay, so in a moment, so I call this technique discrete percolation because in a moment what we'll see is that we're going to design this coupling in an iterative way, starting from the edge in which we're currently disagreeing at. And then we're going to imagine that we're going to grow some kind of like almost like there's going to be an infection process where the disagreements are possibly propagating, and our task will be to tame those disagreements. Okay. Okay.
Yes, matching case, you know the distribution and if you condition on the edge not being there, it's just a match.
That's right.
But if it's there, then it's complicated.
If it's there, then you can think of it as deleting both endpoints of that edge and looking at a matching on the remaining thing. So the first one, you delete the edge. The other one, you delete both endpoints and the edge. That's right. Okay. So that's one of these nice properties of these kinds of distributions. They're like very close. They're closed under very natural operations, like conditions.
This is more sort of hardcore.
So the coupling I'm going to show you, it doesn't. I mean, you can run a version of it, but it's more difficult to analyze, and it will not work for. So here, like there's dependence on lambda that. I mean, you can let lambda be any constant you want. If you apply it to a hardcore model, what you'll find is that there is a specific threshold for lambda beyond which you get nothing at all. And that's related to the phase transition phenomenon I mentioned in the previous lecture. Okay, so our goal is to design gamma, this coupling. And we're going to do it via a local algorithm, starting from the initial disagreement. Maybe let me now change notation to like E, because everything's going to be an edge in this graph. Okay. And then we're going to try to control up or upper bound the expected Hamming distance between two such configurations. Okay. So, right. So maybe the picture is something like this. So maybe I have, say, two. So I'm going to draw two pictures. Okay. So in the left picture, you should think of as I'm sampling, like the matching I get in the left picture should be distributed according to the distribution after I've conditioned on the edge E being in. So this is the edge E. Okay. And then in the second picture, I have the edge being conditioned to be out of the matching. And okay, there might be some other edges in the graph. And I want to now sample the status of all the remaining edges in some iterative way. Okay. And I'll like develop this picture a bit more eventually. Okay. So we're going to be sampling and matching here, sampling, matching here. They should be respectively distributed according to these distributions, but they'll be drawn in a very correlated manner to try to minimize the expected Hamming distance between the expected number of disagreeing edges. Okay. So here's perhaps like the simplest algorithm you can choose. And let me also mention that this algorithm we designed, it does not need to be efficient in any way. It's just purely there for analysis. Okay? So here's an algorithm. Okay, so while there exists some unvisited vertex V incident to some disagreeing edge, do the following. Okay, so I guess maybe the algorithm, I should say that, we want to maintain, we're going to maintain, let's initialize two partial configurations. I say tau and sigma. Tau is initialized to, this edge being in the matching, and sigma is initialized to edge E being out of the matching. Okay, so I'm going to eventually draw tau from the left side, sigma from the right side. Okay. Okay, so now I'm looking at some vertex that sees a disagreement, right? So it has one of its incident edges is already determined, and in one of the pictures it's green, and the other picture is red. And now what I'm going to do is I'm going to just sample from a total variation optimal coupling of all of the remaining incident edges to it. So sample say tau. And maybe let me define one more piece of notation here. So I'm going to let E of V to be just a set of incident edges to V. Okay. So now I'm going to extend these two partial configurations of tau sub E of V, sigma V sub E, E of V. This is from the TV optimal coupling between mu, tau, and then EV, and mu, sigma, EV. Okay, so TV optimal just means the coupling that achieves the total variation distance between these two marginal distributions. Basically, I'm just going to try to, if I'm at this vertex V right here, I'm going to try to sample just the incident edges to it in a way that maximizes the chance that they give the exact same configuration. Okay, and then we'll analyze the probability that it actually propagates a disagreement in a moment.
But for that vertex, it would be 0 the probability, right? So haven't we made the decision already that
for this vertex? So here, in this picture, all these guys had better be not in the matching, right? But here, there's some chance that one of these edges can be added to the matching.
Maybe
Sorry, what's the?
Maybe the question is whether are you sampling on things that you haven't sampled before?
Yeah.
EFV,
Sorry. Yeah.
I guess, yeah. Does EFV include the...
Sorry. Yes. So I should say all the undetermined edges. So previously sampled edges will stay the way they are. Only the undetermined. So, yeah. Sample this.
So the hope is actually get something and then you will say.
Yeah. So we'll never resample an edge on the undetermined edges. Yeah. Sorry. Yeah. Good. Okay. So at the moment this is just some abstract thing. Like we're not constructing this coupling explicitly. I don't know what it necessarily looks like, but well, actually we'll see what it looks like in a moment when we analyze it. But so I'm imagining you're kind of like running like a depth first or like breadth first search here, right? So there's going to be some set of vertices I've already seen, and then I'm going to then look for the next vertex and see like if there is a vertex that is incident to.
Start off with, is V, to begin with is V a visited vertex, or you have just the edge E?
So, right, so when I have just the edge E, all the vertices are unvisited in the beginning. So in this case, if you think of unvisited vertex as one that still has some edges that are not fully determined. So the visited ones are the ones for which all of its edges have been completely sampled. More questions? Okay. Oh, sorry.
That's where we're using like that it's Glauber dynamics with this relatively small lambda because if you're gonna have like some chance that a vertex isn't matched, because if you look at the matchings that contain that vertex, and look at what the probability of that edge deleted, those two are not that different.
Sure, so that fact will come up in the analysis. Although here, this analysis makes no reference to Glauber dynamics. This is actually purely a property of the distribution itself. There's no reference to dynamics here.
Well, I mean, just that there is some chance, because like if you were just like looking at a Markov chain on perfect matchings, you would never, this process would never really convert, right?
Right. I mean, for perfect matchings, they're very simple. Like even on a cycle, where if I run some local Markov chain like Glauber dynamics, it's not even connected. That's right. Yeah. In this case, it will turn out to be the case because of the matching constraint. The fact that I can only have, in this picture, right, even if I add an edge, only one of the edges can be added. And so that will be a crucial part of the analysis. Yeah.
If you're an unvisited vertex, it means there is some edge around the vertex that's not determined, and
Yeah.
there is some edge where it's determined and they disagree.
That's right. That's right. Good. More questions? Yeah.
Does this algorithm also, if you have the sample, you have two graphs on the same vertex set that are close, how to sample optimally matches?
I think you can. Yeah, I think you can turn this into an actual like local sampling algorithm, but maybe we can take that question offline. If that's okay. Yeah.
It's also possible to just sample one of them arbitrary and then just do the entire thing to sample the other one, like sort of try to change one edge and then start propagate that.
Okay. Yeah, there is a slicker way to describe it. It's by I think like Vandenberg and Steiff and then Brouwer and a few others. I like to present it this way because I think it's like somehow like slightly more intuitive to me at least. But yeah, there is a way to make that such a scheme. Like a more direct way to like write down the coupling in like one shot. Good. More questions? Okay. And I guess the final step is of course update tau and sigma, and then mark v as visited.
You may want
Sorry. Yes.
to draw
Okay.
a line there to not go below.
Yeah. Is this line okay?
No.
No, higher. Okay, just basically don't write anymore. Okay. Well, okay, there's like one more step, which is like, okay, technically by the end of this, by the time this while loop terminates, there's a chance that there's still some vertices that haven't been sampled yet. Okay? And if that's the case, you just sample from the TV optimal coupling between them. Okay. Good. So what is happening? Like, what does this thing look like here? So let me like draw a few more edges. Okay, and let's say it's like this, this. Okay, I think, yeah, they are the same. Okay, good. So what does this thing look like? So let's say I'm.
The final step you mentioned would introduce no differences.
That's right. It would introduce no differences. So yeah, very good. So right. So if I look at these two pictures, right? So let's say I'm looking at vertex V, right? And I want to optimally couple. I want to sample the status of these edges and also sample the status of these edges, right? So of course in this picture, right, because this edge has already been included, all of these guys must be red, must be out of the matching, right? And in this picture, I mean, even, okay, independent of what that coupling actually is, like in this picture, I can only pick at most one of such edge to be added to the matching, right? So let's say it's this one, right? So add the green one, and then all the other ones are red. And now, so that's one step of this while loop. Now I can move my vertex feed over here. Right? And now in the right picture, all of its incident edges must be out of the matching, right? And so these will all be red. And in this picture, again, just by the matching constraint, at most one of its edges, incident edges can be added to the matching. And all other ones must be out, right? So let's say it's this one. Okay? So the point of this is just that hopefully you can see that at every step of this coupling, the set of disagreeing edges is always growing by at most one edge, and in particular, it must be either a path or a cycle.
It could be also
Right.
there's no, like, if you pick no one, even though you could have picked one.
Yeah, that's right. In which case, yeah, I mean that's only good for us, right? That's right. So, was there a question? Okay. So that's really the key observation, right? And then the whole question then is, how can you bound the probability that at least one new disagreement appears? Okay, so key observation. Key observation. The matching constraint implies that disagreements grow by at most one. At most. In each step. Okay? And also the set of disagreements is either a path or a cycle.
This means that once you've reached agreement, you can continue with them being equal.
Once you've reached agreement, you can continue. So, right, so by the time you exit this while loop, right? Okay, yeah. So let me also say the comment that Abhishek mentioned earlier, which is like, okay, like by the time you exit this while loop, what you'll have found is you have a set of disagreeing edges, and they'll be completely surrounded by edges which are all guaranteed to be not in the respective matchings, right? So that's the same, you can just like splice it out, and now you just have the same graph, and you can perfectly couple the two pictures, right? So the point is that the moment this while loop terminates, no new disagreements will ever be introduced, right? That's it, right? So key observation. Also, when, okay, start this. When while loop terminates, no new disagreements. You can couple remainder perfectly. Right? Okay, so really all that's left to do, so this is like some kind of infection or percolation process, which is very easy to tame, right? You're only infecting at most one neighbor in each step, right? And so all that's left to do to get something quantitative, like a quantitative bound like this, is to just upper bound the probability that there is some new infection, right? Okay, good. So the next claim is that in each step, the probability of new disagreement is at most, say, lambda times delta over 1 plus lambda times delta. Okay? Okay. So what is this probability of introducing a disagreement? Well, again, in one of the pictures, I'm essentially fixed, right? In one of the pictures in which the incident edge is in the matching, all of its other edges must be out. So it's really the probability of new disagreement is really just equal to the probability that V is matched under one of the two distributions. Let's say U condition on tau. Right? Okay. So how do you prove this inequality? So this thing is, of course, equal to the summation over all its neighboring vertices, U, of the probability that V is matched, or let's just say UV is in the matching. Right? Okay. Now I claim there's also like just one very quick identity, which is that the probability that UV is in the matching. I claim that this is exactly equal to lambda times the probability that U and v are both unmatched. What I'm trying to do here is rewrite each of these probabilities back in terms of this original probability I'm starting with. Okay, this looks maybe perhaps slightly strange, right? But it actually has a very simple explanation. It's just that, any matching in which u and v are a match, I can always create a matching in which u and v are matched together just by adding that edge uv, right? And when I add that edge uv, I introduce an extra factor lambda, just coming from the definition of the distribution I'm working with, right? So what does this mean? So this is the same thing as lambda times the probability that u is unmatched, condition on v being unmatched, which is at most, so since this one, times the probability that v is unmatched. This is always upper bounded by lambda times, just because this one is at most 1, times the probability of lambda times 1 minus the probability that v is matched. Okay, so what all of this tells us is that the probability that v is matched is upper bounded by the number of neighbors times lambda times 1 minus itself. And so if you then rearrange, you get the inequality, right? So delta times lambda times 1 minus the probability of v. Yeah. Is this okay? Questions about this? Okay.
The distribution is only used in the first equality.
Say again? The actual distribution is only used here. Yeah.
Not the entire.
Yeah.
We also used it in when the while loop terminates, no new disagreements.
Right. So, yeah, but this fact is like really generalized. It's really just conditional independence. Like the ones you have. Yeah. More questions? Yeah.
So coupling has been used for like a long time to analyze mixing, and is somehow the win here is that we don't actually need to do coupling on our like Markov chain, but we get to do coupling on some algorithm that we make up.
That's right. We just need existentially some coupling that we can analyze, right? This thing did not need to be efficient by any means, right? So, right. So maybe a little more about Salil's comment, which is that if you use like classical coupling-based techniques for proving Markov chain mixing, like I take Glauber dynamics and I couple two copies using a Markovian coupling, you will find that there's again some threshold of lambda beyond which your coupling just doesn't contract anymore. It doesn't work at all. Right? It gives you nothing whatsoever. Okay? But somehow, like when you switch this perspective, when you're trying to couple something like the conditional measure, which is what you need in spectral independence, you can the world opens up to you. Right? You can also construct this coupling between the two conditional measures using a Markov chain if you'd like, but you can do many other things. Any more questions? Because I'm about to switch gears. Okay. Good. So now I want to talk about like a totally different method, something that's just not probabilistic whatsoever. But I think it illustrates like a very nice and beautiful connection between probability and like something more algebraic. Okay. Pictures, so maybe I'll just erase. Okay, I'll just erase the calculation. Okay. So the other method I wanted to tell you about is this method via the geometry of polynomials. Okay. So what we're going to do is we're going to encode mu via its generating polynomial. So g sub mu of z. So there's one variable ze for each edge in the graph. It's going to be a summation over all matchings. U of m, z to m. And here, of course, I mean the product over all the edges in the matching, z sub e. Okay. And there's like this very broad theme in geometry of polynomials where you try to deduce probabilistic information about your distribution mu by studying properties of this multivariate polynomial, g sub mu. Okay? So you have a polynomial, you can ask for its zeros, you can ask for whatever you like. Right? So this theme, so analytic, sort of algebraic properties of g mu imply properties for mu. And I'll illustrate some examples in a moment. Okay. So for example, I mean, one of the key observations, and it's a very simple observation, is that if you differentiate the logarithm of this generating polynomial, you can get out things like the marginals, the correlations, and so on. Right? So for instance, if I differentiate with respect to z sub e of log g mu, and let's say I evaluate it all once, this is exactly equal to the probability that I sample a random matching from the distribution mu that this edge E occurs in the matching. Right? And that's just because, if I chain rule this thing, this is equal to the derivative of g mu itself divided by g mu. Right? And in the numerator, differentiating by the variable zi just kills all the terms, all the monomials that do not have the edge E. Right? I guess here we're also using the fact that it's a multilinear polynomial. Okay? All right, so this is one observation. The second observation is if I differentiate again, I can then get pair correlations. So the derivative with respect to ze and say zf, log g mu, all ones, this is going to be equal to the probability that both edges E and F occur in the matching minus the probability that edge occurs in the matching and the probability that F occurs in the matching independently. And again, this is just by chain rule. Right? So already we see that this polynomial encodes a lot of the things that we care about, right? Like pairwise correlations. Okay?
Almost the same matrix.
Almost the same matrix, up to multiplying by a certain diagonal matrix that has just like the variance of the edge variables. That's right.
This is the symmetric matrix.
So yeah, this is the symmetric version. Yeah. Well, it's like unnormalized in some sense, but yeah. Yeah. Okay, so, all right. So now let me erase this. So I guess, for this part, since the emphasis is going to be about the connection between the polynomial and spectral independence, I'm going to take for granted that the matching polynomial has well understood zeros. Okay, so there's a classical theorem of Heilmann and Lieb in statistical physics that basically tells you everything you want to know about the zeros of the matching polynomial. Okay. Okay.
When does that date to, roughly?
Heilmann and Lieb?
When, yeah.
Oh, like 1972, I believe. Okay, so I'm going to take that for granted. And I'm going to just tell you about, so maybe I'll tell you like some examples of theorems that can be proven that connect the polynomial to correlations. Okay, so there's a very nice theorem of Borchea, Brandin, from Liggett, 2009, which I think illustrates this theme very well. It states that if G mu is non-zero whenever the imaginary part of Zi is positive for all I, then mu satisfies very strong negative correlation properties. In particular, then the probability, let's be consistent, let's say CE is E. And then for all E and F, the probability that F is in the matching, the most, the probability. Okay. Sorry, I guess I shouldn't use matching here because matching doesn't satisfy this assumption, but this is a general theorem about, if I encode any distribution on, let's say, subsets, and I, look at its corresponding generating polynomial, this theorem is true. Okay, so this is a property known as real stable. These polynomials were, instrumental in, like, for instance, the resolution of the Katz-Singer problem, and also have connections in the study, like in this whole line of work on interlacing families. And yeah, they have, this property also has very strong probabilistic consequences. Okay, so from something purely, zero freeness in the upper half plane, you can get negative correlation. So examples of applications: a uniform distribution over spanning trees. Okay. You can apply this theorem to this distribution. Okay. Okay. And actually, maybe I should have written this earlier. So maybe also just like one observation, just coming from this key observation, or so maybe I'll call it a lemma, which is that if, let's say, I look at the Hessian of the logarithm of G mu, and I know that it's like spectrally bounded. Okay. And let's say I assume, and there exists say some constant b such that the probability, the marginals are, it's not too biased. Mu is order of alpha b, b alpha, spectrally independent. Yeah.
Is there some reason we might expect this theorem to hold? Like why should the imaginary parts?
Some like intuition for this. Good. Let's pass into it. Okay, so like I guess the way I kind of think about this is that typically, the two variable case will like give you like the right intuition here, and like in the quadratic case, you can like verify it very easily just by using like quadratic formula, for instance. But yeah, a lot of this it has a very strong local global favor where you can kind of reduce it to like at least a two variable case has like intuition.
I mean, one thing to say is that like it was kind of univariate and you had no roots in the upper half plane. It's real rooted. And then this inequality is some generalization of what you would get from like the discriminant being non-negative.
Yeah.
So this is some kind of generalization of the fact that for real rooted polynomials, the discriminant's non-negative.
Okay. Yeah, that's a much better answer than mine. Questions? Okay. But the actual theorem that I want to actually prove to you, okay, that's good, is a statement that requires much weaker zero freeness, but then gets also a weaker conclusion. It's just that the spectral independence parameter is bounded by a constant. So like this thing I showed you last time, I think, in one of the examples, that if you have such strong negative correlation, that gives you one spectral independence. Here's the actual theorem I wanted to prove to you. This theorem, like there was a version of this that's due to Alimo Hamadi, Anari, Shiragur, and Wang from 21. And then we had some generalization with Zhongchen and Eric Pagoda, which says the following. That, yeah, if I weaken the zero freeness statement, I can still get something interesting, get a spectral independence bound. Okay, so if G mu of Z is non-zero whenever, let's say, Z is in a disk of some radius, some small radius, little delta, around the point 1, let's say, and the distribution is not too unbalanced, and exists B, such that for all E, the probability that E is in the matching, and most B, so this B strictly less than 1 is strictly positive, then mu is order of 1 over delta squared B1 minus B. Spectrally independent. Okay, so I guess the original theorem of Ali Mohammadi, Anari, Shiragu, and Wang was if you assume zero freeness with respect to a sector, you can get a stronger version of the spectral independence where it does not require a bound on how balanced the marginal is. Here we're assuming very weak, which is just zero freeness with respect to a small constant radius disk around the all ones point. Sorry? Which lemma? Oh, this lemma. Sorry. Yeah. So it's essentially just what you had observed previously, which is that the entries of this matrix, they're exactly the Hessian.
Sorry, my question is this theorem just calculus given the lemma?
Oh, given this lemma. Oh, sorry. No, these two theorems are not related to another, right? So this one I was just mentioning because this is. I guess I forgot to finish the thought, which is if I assume a spectral inequality on the Hessian of the logarithm of the generating polynomial, there is a particular application. In the case where alpha equals 0, this is the log concave, and has application to matroids. So I just wanted to mention that there's another very natural analytic property of the polynomial that will give you something. But this theorem and this lemma are not related to one another. Yeah. Good.
One improves with B, the other one gets worse with B?
Sorry, wait a second. Oh, sorry. No. Yeah. No. Yeah. This should degrade. More questions? Okay, so in the remaining time I have, actually, fortunately, the proof of this is actually fairly short, so and sweet. Okay, so the key ingredient that we'll need is something called, there's a nice lemma in complex analysis, which is the Schwartz lemma. So it says that if I have a holomorphic function f mapping the disk to the complex plane such that it's nicely bounded. The absolute value of f of z is upper bounded by 1 of z. Then I can automatically, from the boundedness of f, deduce a bound on the derivative of f. So okay. And I want to use this to bound the spectral independence of the distribution. Okay. So in particular, I'm going to try to construct a little f based off of the generating polynomial and the fact that differentiating the generating polynomial gives me these correlations in a way that satisfies the conditions of the Schwartz lemma, and then I can invoke this bound as just as a black box. Okay, so how are we going to do this? So what we're going to do is we're going to construct functions. So we're going to define, so we're going to first let f of z. So again, we're fixing an I, or an edge E, let's say. And we're defining a function f as just being the derivative with respect to the edge E of log of the generating polynomial. And then for technical reasons related to some normalizations, I'm going to divide by the probability that E is in the matching times the probability E is not in the matching. Okay. Yeah. Okay, actually, maybe just for simplicity, let's not divide by this, because we've assumed that everything is bounded by a constant. Anyways, all the marginals are bounded by a constant, so let's just ignore that for simplicity. Okay. The point being that if I differentiate this function f with respect to any other coordinate, that's again going to give me, by this, the correlation between E and f, right? And from this, I want to construct a little f, a univariate function, little f. Okay, so we're going to let this. We're going to construct. So I guess first comment about f, where is it well defined? It is only well defined in the region in which log of g mu is well defined, which is exactly where we're going to use the zero freeness of g mu, right? This only makes sense if g mu is zero free, right? So we're going to construct functions, say phi 1, phi n, mapping the unit disk into the zero free region. Okay, and I'm going to allow myself like an epsilon of room, so I'm going to divide by delta by 2. Just for convenience, okay? So crucially, this is the zero free region on which log of g mu is well defined and holomorphic. Okay, and we're also going to construct a function psi that maps sort of like the image of f back into the disk, right? Because I need to satisfy this boundedness property, okay? F back into the disk, okay? Maybe I'll move this on. Okay, so how are we going to construct these functions? We're going to do it basically as simply as possible, right? So I'm just going to take affine functions. So I'm going to take phi of I of z. I want this to be equal to 1 plus delta over 2 times a certain sign term, which I'll tell you in a moment, like why we need this sign term. This S sub j, this is just equal to the sign of the influence basically this is how I'm going to get a control on the sum of absolute values of the influence.
I is E.
Sorry, yeah. Sorry, I apologize. Yeah, so let's say E, say F. E and F. Yeah. And also, I'm going to let psi of z to also be a linear function, say delta over 2 times z. Okay. And now I'm going to take little f of z. It's going to be a psi applied to f, applied to phi 1 of z, phi n of z. Okay. So if we just calculate by chain rule, like assuming we have satisfied the assumptions of the Schwartz lemma, then we know that 1 is an upper bound of f prime of 0, which by chain rule, this is equal to, I have a delta over 2 coming from the derivative of psi times the summation for f of the derivative cf of capital F times s sub f. And I guess I have a delta over 2 squared. Right? And this thing here is exactly the influence. Or I guess I should say this thing here. Okay, but up to a constant, this is the same thing. Right? And so if I multiply by its sign, I'm just going to get the absolute value. Right? Right? And now if I rearrange things, it just exactly tells me that the sum of the influences is upper bounded by a constant, depending only on the radius of the zero-free region. Right? So the only thing I need to verify for you is that it satisfies this key assumption in the Schwartz lemma, that actually this function maps the disk back into the disk. Okay, and that's where that's in particular why we're sort of scaling down things with this function psi. Questions about?
Upper bound on the values of f?
Sorry?
Can you repeat why little f is norm is bounded by 1?
Right, so assuming little f satisfies the assumptions of the Schwartz lemma, like assuming it satisfies that the function itself is bounded, then the Schwartz lemma tells me that, right? And I haven't proven to you why it satisfies the assumption of the Schwartz lemma. That's the final step. Yeah.
What is f in the definition of psi?
Oh, I'm sorry. Yes. Okay. So I guess I shouldn't keep you. Also, I'm sorry. I'm overloading the notation for little f. Yeah. So let's call it like g. So g is like some other edge, right? So in the definition of capital F, I've already fixed some edge e, and now I'm looking at its influence on some other edge, little g. Yeah. Sorry about that. So yeah, I should not overload the little f. Say little g, little g, little g. Okay, actually, I'm sorry. I'm going a little bit over time. Like 3 minutes, hopefully. Sorry. Okay. Okay. So the proof of the fact that f maps this little disk into another disk of, let's say, some bounded size, right? If I can prove this, then the fact that I'm now scaling things down by delta over 2 is going to allow me to satisfy the assumptions of the Schwartz lemma, right? So I just need to prove this, right? So suppose Suppose not. Right, so then there exists some y. Sorry, let's see. There exists some z1 and the zn in this little disk, and some y satisfying, or let's say with the normal y strictly larger than 2 over delta, such that g mu of z is equal to y. Right? Now this left-hand side here, again, just by, or sorry, f of z. Right? Now this left-hand side, because it's the derivative of log, I can now just write this as the derivative of z sub e of g mu of z divided by g mu of z. Right, and I want to use this to contradict my assumption that g mu is zero free. Right? So if I rearrange, this is the same thing as saying that, so I multiply g mu on the right-hand side and I divide by y on the right, on the left. This is the same thing as saying that g mu of z minus 1 over y derivative with respect to ze of g mu of z is equal to 0. Okay, this might look slightly strange, but now here's basically the punchline, which is, okay, I can write this back entirely in terms of g mu just by using the fact that g mu is a multilinear polynomial, right? So you should think of this operation as replacing the variable ze, where e is this distinguished edge that I've picked out, by ze minus 1 over y. And 1 over y is a small perturbation because I assume y is large, right? This is equal to g mu of z, everybody except e, and then I have ze coming from this term minus 1 over y here. And now the point is that ze, and I assumed it's a point that's very close to 1, and 1 over y is a very small perturbation of size delta, right? So this is still inside the disk of radius delta. I guess I chose the delta over 2 just so they add up to delta. And now I've constructed a set of inputs, all satisfying, all being within this region, that give me 0. And that contradicts the zero freeness that we start off with. Okay, so hopefully this illustrates like two interesting and very different techniques for establishing spectral independence and how it connects to like now many other fields. But yeah, sorry for going over time, but thanks for your attention. Good. So in the first proof, the question was, where do we assume that the maximum degree is bounded by a constant? All right, so in the first proof, we needed the maximum degree constant because that is how we bounded the probability that there is one new disagreement introduced in each step of the algorithm, right? Because if you imagine you have many unbounded maximum degree, right? Then you should intuitively, there's a higher chance that at least one of them is going to be included in the matching, right? You have more options to pick from, right? So that was crucially used, and the bound of the probability that a disagreement is propagated. Here, I haven't told you exactly what the zero freeness property that the matching polynomial satisfies.
In the marginal.
Sorry?
In the marginal assumption.
It will also be used there, but here also the matching polynomial satisfies, the zero freeness for the matching polynomial also depends on the maximum degree. For those of you familiar with the Hamann and Lieb theorem, this might sound slightly strange to you, and that's because the specific form of the matching polynomial that we're working with here is not exactly the same as the one that's used by Hamann and Lieb. Okay? So maybe I'll just write it down very quickly. So all right, I can draw for you what the zero free region looks like. Here, we're looking at the G mu sum over all matchings. And the zero free region for this looks something like this. It's parabolic. And the width here is like 1 over polynomial in the maximum degree. Okay, so this basically the size of the zero-free region is shrinking as you increase the maximum degree, and that's going to show up in the little delta you have.
And this is like appealing to Heilman and
Okay,
Lee,
so the actual
or-
proof of this does not actually appeal to the Heilman and Lee. It uses something related, which is the Asano-Rel contraction, which is maybe a way to prove Heilman and Lee.
But like using different tools and properties of matchings and.
I mean, ultimately, it's really the same tool, Asano-Rel contraction. But yeah, Heilman and Lee works with a slightly different form of the matching polynomial where the variables correspond to the vertices instead of the edges.
I meant it's using different tools than the other methods we have for proving spectral independence.
Yes, very different. Yeah.
So if X degree is unbounded, then can we still sample?
Yeah, so this is also coming back to this comment that Salil had in the beginning, which is there's a very classical result of Jerem and Sinclair that allows you to, that shows Glauber dynamics mixes rapidly even for any graph, but using a very different method. So this is using something called canonical paths. And it gets like, n squared m or something like this, and polynomial dependence on lambda as well. Yeah.
I thought that result actually required like a minimum degree.
Minimum
That
degree.
was like the early versions. That had
You might be referring to
minimum
like,
linear degree.
maybe you're referring to like the perfect matching result where they needed,
Oh,
it only
okay,
works for
yeah.
dense graphs. Yeah.
Oh,
I think if I understood, yeah. Have it right.
So let's thank Kuikui again and for the speakers of all these mini courses. I really enjoyed learning a lot of new stuff this week. So thank you.